There are many obstacles that can block the path to a successful software project. When you come across one, it helps to think like a seasoned hiker and follow the trail marked by blue blazes around the problem so that you can get back on course and keep moving forward. Welcome to Blue Blazes Podcast. I'm your host for the journey, Jay Tower, and I'm a partner and principal consultant at Trailhead Technology Partners. In this series, we talk with industry experts who share their best tips for avoiding the pitfalls on the path to successful software projects. My guest on this episode of Blue Blazes is Neal Ford. Neal is a director and software architect at ThoughtWorks. He's also an internationally recognized expert in software development, focusing on agile engineering techniques and software architecture. He's authored 9 books, including Fundamentals of Software Architecture and Building Evolutionary Architectures. You can find him sharing his expertise at software events around the world, as well as on his website, nealford.com. During our conversation, Neal and I discuss how architectural fitness functions are like unit tests, but for your system's architectural capabilities instead of its behavioral capabilities. We explore how incorporating these functions can help ensure characteristics of your application, such as performance, scalability, maintainability, and security. It's an important conversation and one I enjoyed having, so I hope you enjoy listening in. Well, hello, Neal. It's nice to meet you, and welcome to the Blue Blazes podcast.
Thanks for having me. It's a great pleasure to be here. I'm wearing the appropriate shirt for it, apparently, so it's good.
Yes, that's right. You're on brand, so thanks for doing that. Well, today we're talking about something that is somewhat new to me, which is something called fitness functions or architectural fitness functions. I've been lucky enough to hear a little bit of your talks and things that are online and read some of your books that mention architectural fitness functions and describe them, but I don't want to assume that the listeners here are totally familiar with that yet. So would you mind giving us a quick introduction to what is an architectural fitness function?
Absolutely. So this is a term that we coined in the first edition of Building Evolution Architectures, which came out in 2017. The second edition came out in last November. This is actually an insight by Rebecca Parsons, who was one of my co-authors, who is the CTO emeritus at ThoughtWorks. When I first met her at ThoughtWorks, she was working as an architect and enterprise architect, and she has a background in building genetic algorithms. And one of the things that they have in the genetic algorithm world is this idea of a fitness function. So if you're trying to gently guide the way a genetic algorithm mutates, you have a fitness function that says, okay, here are the desirable outcomes I want to have. So it builds sort of guardrails around your genetic algorithm. Rebecca had the great insight of, that sounds like a really good mechanism for governing software architecture characteristics. And the evolution in particular of software architecture characteristics. And so when you think about, let's back up a second. Think about structural design and software architecture. There are 2 main activities you have to do there. One of them is requirements in the domain, the problem domain. Obviously, the thing that we're writing software about is going to heavily influence the way we structure our architecture. But the other thing you have to think about, what kind of capabilities does this system need to support, like scalability or elasticity or security, or all those other capabilities, which are not strictly part of your problem domain, but are sort of meta things that it needs to support to be successful. That's what Mark and I refer to as architecture characteristics. So if you look at the domain, how do we manage the regression of our domain to make sure that as we build things, we don't break the stuff that's already there? We have a lot of mechanisms. We have unit tests, we have functional tests, we have user acceptance tests. If you're a big enough company, you have an entire department called QA that their only job is to make sure you haven't broken something that already works.
Right.
What we need is a similar mechanism for the architecture characteristics. Now, a lot of projects do that ad hocly because they're looking at performance or something like that. This idea of an architectural fitness function is like a unit test, but for an architectural concern instead of a behavioral concern. But it's broader than a unit test because the unit tests are great for doing things like assessing internal code quality and structure. You can do that on a code base with a unit test. But I can't test scalability with a unit test. I can't test performance with a unit test. And so those require monitors. And so the idea of an architectural fitness function is broader than just a unit test. It's a way of objectively assessing some desirable architecture characteristic in your ecosystem, whether that's performance or scalability or security or elasticity or one of those things. And they run just like unit tests. So these wire into your build so that you get continuous feedback, because part of the benefit of unit testing is if I make a structural change and break something, as soon as I try to check that code in, I fail a unit test and I can fix it right away. Well, on a
Mm-hmm.
lot of projects, if I make a change that accidentally degrades performance and I don't find out for 6 months what that change was, and now we measure performance like, oh man, performance is terrible now. What did we do to break it? Well, now we've got 6 months of pull requests to look through to figure out which one broke it, versus
Right.
every single time you make a change, you validate it by running a performance fitness function. And now you know the day that you changed it, oh, that's the thing that broke it. So the essence of software development, particularly agile software development, is fast feedback. And this is a
Mm-hmm.
way to get really fast feedback on the critical capabilities in your architecture that you need to be able to support to be successful. So that's the essence of this idea of fitness functions. When we talk about evolutionary architecture, we talk about the mechanics of evolutionary architecture to evolve and then the structure required. Fitness functions are the mechanics that allow you to make changes to your architecture without worrying about accidentally breaking security or performance or something like that.
Mm-hmm. Well, that seems really powerful to me because I feel like the majority of software projects, the ones that are not using a fitness function right now, they have these requirements, which are, the actual features that the application is required to do to be successful. And then oftentimes it goes as sort of an unwritten rule or an unwritten hope, I think, that it'll be
Hope.
scalable, maintainable, performant, etc. Right? But often those are just the things that are kind of in the back of everyone's mind. I assume you guys will make this secure, you'll make it performant, you'll make it easy to maintain. And of course, we know that that's not always true in software projects. So putting those on the table and then actually testing them seems really powerful to me as a way to, make sure it's happening.
Well, it's a great way to be. So we are always interested in an engineering approach to software development. And the engineering approach here is to build something that's measurable and then measure it versus
Mm-hmm.
just, as you say, hoping that, it's going to work out okay. But the
Mm-hmm.
other important thing here that I want to touch on right now is a common misconception about uh, the difference between what we call emergent design versus evolutionary architecture. So one of the things the design community will tell you is that you should not start off designing a lorry. Instead, you should start with a roller skate and then make that into a unicycle and then a bicycle and then a motorcycle and a car and a truck and then a lorry. Kind of
Mm-hmm.
immerse the design based on what you learn along the way. And that's great for design. And I strongly encourage that. But you can't do that with architecture, because architecture is about capabilities. And a roller skate does not have the same capabilities as a lorry in terms
Mm-hmm.
of weight and distribution and distance and all those kind of things. And so you have to have planning in architecture. You can't just let it emerge like you can design. To your point, you can't just start emerging a design and hope that it'll be scalable and performant and elastic. I mean, if it's a simple enough project, then you don't care about those things. But if you're building a complex project, you need to care about those things fairly early on. And one of the things that we coin in our book that we're actually seeing an uptick in is this idea of fitness function driven architecture. Just like test driven development, this is fitness function driven architecture. Rather than make performance testing a post hoc activity, why don't we build the performance fitness function first
Mm-hmm.
and then build our system within those guardrails? Then we'll never worry about whether we've achieved performance or not, because we did on day one, or it failed until we achieved performance, and now we'll keep that green for the rest of its life. And so it's a very engineering centric way to both identify those things. A lot of people identify the capabilities they want, they just never test them, or they test them in a
Mm-hmm.
completely ad hoc way. We need a faster feedback loop for these things. And so that's
Okay.
really the essence of this idea of fitness functions, is really fast feedback for architecture changes.
Yeah, I've seen a lot of applications where the like poor man's fitness function is, do the users feel happy with how fast the system is responding? It's
Hmm.
pretty hard to measure that and compare it over time, though.
Well, especially if
So
you
you
have highly variable users that some of them are happy and some of them are miserable, then how do you split the
exactly.
difference?
Yeah, there might be some users that'll never be happy with the performance, no matter what, right? Well,
A huge subset, I'm sure.
yes. Well, you mentioned metrics a lot there. And obviously, I think these fitness functions are only valuable if there's something actually measurable.
Hmm.
Some of those are harder to get than others. I can imagine an easy one being like the response time of an API. You want
Yep.
that to stay the same or get better over time, not to get substantially worse with some new code change.
Hmm.
There's some that are harder though. Code maintainability comes to mind.
That's a
So,
perfect example. I'm glad you brought that one out. It's perfect because this is
great.
what Mark and I referred to as a composite architecture characteristic. So we
Uh-huh.
are big advocates of boiling architecture characteristics down until they're objectively measurable.
Mhm.
Maintainability is a great example of that because what is the objective measurement for maintainability? There isn't
Yeah,
one. But
exactly.
does maintainability, is it composed of things we can measure?
Hmm.
Turns out it is. Deployability is one aspect of maintainability. We can measure the rate and success of deployability. How testable it is an aspect of maintainability. The
Hmm.
coupling characteristics of my code is an aspect of maintaining. So that's part of the game you have to play as an architect, is take these composites and actually
Hmm.
decompose them into things until you get to leaf nodes that you can objectively measure. That's actually valuable in two ways, because one, it gets you away from these vague terms. I
Hmm.
want high performance. Congratulations. I have no idea what that means.
Right.
You got to give me a number. I want it to be maintainable. Great. What does that mean? I
Yeah.
can't measure that. That's not an engineering term. That's a happy aspirational goal, which is great, but you boil that
Hmm.
down. And so that's part of the analysis phase of looking at those kind of things and saying, okay, of maintainability, which is the really important stuff? Is it reliability? Is it maintainability? Is it data integrity? Is it deployability? And that focuses your efforts on the things you should put effort into writing fitness functions for, without trying to carpet the entire world with them.
Yeah. Yeah, I can see that making it forcing you to define things, making it much more measurable.
I would go one step further about this as well.
Hmm.
So I'm sure everyone who's listening to this is familiar with the concept of, in domain-driven design, of ubiquitous language. That's on a software project. You want to make sure that when you're using technical terms, everybody agrees on the definite, objective definitions for those terms.
Hmm.
I extend this to say that within an organization, the architects in that organization should have a ubiquitous language when talking about architecture characteristics. I see too many organizations where architects in different divisions are talking past one another because they're saying performance, and one of them thinks it's request response time, and the other thinks it's first contentful paint. Those are
Hmm.
very different metrics, but
Hmm.
performance could be any of those things. And so
Right.
I think it's really useful within an organization for the architects to get together and boil down a bunch of objective measures that we care about as an organization, and
Yeah.
use those as engineering terms and not these sort of vague things that you want
Mm.
to do. And that cuts down on a lot of churn at the architectural level, and it gets you closer to unifying around some common engineering terms
Sure.
and goals.
You compare this to other types of engineering, building a bridge, for example, when they talk about being able to handle heavy loads on the bridge. They have a very specific definition of that, hopefully, when they're
Well,
building that bridge.
that's a great analogy, actually, because my first major was not, it was actually journalism, but then I
Yeah.
quickly moved over to mechanical engineering.
Mm.
And I spent just enough time there to do all the maths for both static and dynamic weight bearing, and it gave me the appreciation, man, those guys have a lot of sophisticated math to do all that
Hmm.
stuff. In the software world, I think we are still at the stage they were, where we build a bridge and roll something heavy over it and it collapses, and well, that wasn't a very good bridge. Let's build another one. So,
That's right.
and we'll eventually get to that level of sophistication, but give us a few thousand years. We're just not quite there yet. I was actually
That's right.
talking to somebody in Europe that said that in their village, literally the way they used to engineer bridges is to build a bridge and then roll the heaviest vehicle they had slowly across the bridge to see if it hold up. And if the truck made it across, it was a good bridge, and we're good to go. So that's kind of where we are in software now. But we're getting there.
Yeah.
We're learning some more actual engineering and software. So we'll eventually get
It
there.
is improving. We've been building bridges a lot longer than we've been building software.
Yeah, a few thousand years versus charitably a few hundred years for software. So, but give us time.
Yeah.
We'll get there. It's going to look different than the kind of verifications we have in traditional engineering. In fact, this is one of the observations I made many years ago, that people keep thinking we're going to invent a calculus for software like they have, but we don't
Mm.
need that in software. The main reason they have calculus and that kind of engineering is because it's crazy expensive to build their stuff.
Mm-hmm.
Our stuff is soft. It's really cheap to build software and test it. And so,
Yeah.
my opinion, testing is the engineering rigor of software development. It's not
Yeah.
the pre-analysis, it's the analyzing what's actually running, because we have so many powerful ways to test our things in realistic scenarios that I think that is going to be a better verification mechanism for us than any sort of calculus that we invent, at least in the
Yeah.
near term.
Yeah, that makes sense. Really, all other engineering is focused on hardware of some kind,
Exactly.
except for
And
software
our things
engineering.
is soft. It's very soft.
Yeah. Interesting. Hadn't thought of it that way before, but yeah, now that you mention it, it seems obvious.
Yeah.
So
I stole that from a great design paper that talks about the difference in software and hardware, and it was very influential in my thinking about this as well.
Very.
Because the point of that paper was that our construction technique is the source code. That is that's the blueprint of the entire building is our source code, and we manufacture it instantly by clicking a button. And we can change our blueprint almost instantly and then remanufacture it by clicking a button. You know how happy civil engineers would be if they could play what if games and click a button and a new bridge would appear? They'd be the happiest people in the world, and would have the most complicated bridges you've ever seen in your life, which is why software is so complicated.
Yeah, we have a pretty different world than our siblings and other engineering.
But that brings up an interesting point about the fitness function stuff that I want to make sure that we get in at some point.
Sure.
And that is, so when we first started talking about this fitness function thing in 2017, most of the interest was in these kind of operational things like scale and elasticity, because that was the early days of microservices, and that's what everybody was really interested in, is, super scale. And so a lot of interest in that kind of stuff. And we would talk about these internal code quality fitness functions like psychometric complexity or normalized distance from main sequence, abstractness and instability. And mostly we got sort of yawns from developers like, yeah, we know we should do all those things, but we're pretty good software engineers. But in the intervening time, what we've realized, and this is my new mantra, get ready for a tsunami of working but terrible code that's been generated by Gen AI and LLMs. It works, but it's awful. And so we need to get a handle on governing that stuff. And that's where these internal code quality fitness functions are going to be critically important, because AI doesn't understand abstractions well. AI wants to solve things with brute force. We understand abstractions. And so when you're allowing AI to generate code, it's going to generate with brute force. And so we need fitness functions in place to look at things like psychometric complexity, things like coupling, because it's going to create the worst, awfully coupled code in the world. It's going to be up to us to refactor that into properly abstracted code. One of the things that we've seen already is that project use pull requests have gotten bigger since people have started using ChatGPT, because AI solves things with brute force. So all those internal code quality fitness functions that people used to sort of yawn about suddenly are very important, because now these are the guardrails you put around generated code in AI to make sure that it functions okay, but does it also meet the capabilities I want? Because what happens if the Gen AI generates code that behaves correctly and it's 10 times slower than you need it to be?
Right.
We need both those things in place to be able to massage and build literally governance guardrails around generated code. I think that's going to become a big important thing in the near term. I believe that the role of developers is already in starting to shift between writing a lot of code versus refactoring generated code. I think
Hmm.
the refactoring menu item in your IDE is going to get a whole lot more work than it used to,
Yeah.
because I think we're going to be doing a lot more massaging of code than actually writing
Interesting.
code. And I think we're almost to that tipping point already.
As fundamentally as statistical models, these generative AIs are, predicting the next token or word that is the most likely next word, which sort of by definition means that it's generating the most average code
But
possible for you.
it's
Yeah,
the most statistically likely code.
exactly.
And
Not
that's
the
why
best.
people get fooled by it, because it turns out that correct things are also statistically likely most of the time,
Yeah,
but not always.
exactly.
And it doesn't know. It's just a big pattern matcher. So
I've done enough software development, in the last 25 years to know that the most likely code somebody's going to make and good code are not necessarily the same thing at all.
Well, and the other important thing about that is that the things that AI are really good at solving are things that have a massive corpus of solutions out there,
Hmm.
and statistically, hopefully, you'll get the cream of the crop will sort of rise.
Yeah.
But that's exactly the problem with software architecture, is that architecture decisions are often one off, because this has never existed quite in this way before.
Yeah.
So that's why AI is terrible at architecture decisions, because there's no corpus of learning that it can slurp and do pattern matching off
Sure.
of to get statistically correct answers.
Seems like another way that software engineering is different from the other types of engineering. Lots of bridges have been built that are basically slight variations on each other, but fundamentally this exact same bridge,
Yep.
just in a different location, right?
Mhm.
But software projects are never the same as each other. Well,
Exactly.
I want to get to something important question, I think, for somebody who's maybe new to this concept, Neal, which is you compared it earlier to unit tests a few times, and I think that's maybe for a beginner a really great way to understand the concept to start out with. These are like unit tests for architectural capabilities,
Mhm.
and yet unit tests. If you think about the hierarchy of testing, usually unit tests are the fast, simple ones that you run at development time, and then you go down that stack and there's the longer, more complex tests like integration tests or load tests or things like that run less often or later on in the process. But it
Mhm.
strikes me that based on the ability to generate these different metrics, like uh, response time is one that you can only really generate in a live application versus cyclomatic complexity, which is something you could do at development time. So
Yep.
in that comparison with unit tests, maybe does that analogy break down a little bit when it comes to where and when you do
It,
these
it,
fitness
it
functions?
does, because I mean we're trying to create a simple analogy here, but it
Hmm.
falls apart really quickly, because exactly to your point, some things can be run at compilation time. So we actually have a series of when it's most appropriate to run these things. We have categories. An atomic fitness function is a very narrowly scoped one that can be run at compilation time, versus a holistic fitness function is one that requires more resources or needs a production environment or production like environment. So we've actually categorized these in terms of when you can run them, and how often, and what the impact is on your project, and that sort of stuff.
Yeah.
So rather than say it's like a unit test, it's like the entire suite of tests that you have. But again,
Hmm.
that's misleading, because none of your tests require a production environment to run, whereas performance, scalability, elasticity, availability all need a production-like environment. So, but
Hmm.
that's one of the reasons why fitness functions are fundamentally more complex than your normal testing, because it's all in one tech stack. It's
Hmm.
whatever testing tool you decided to download and use for your project. This may require a monitor, it may require testing frameworks, it may require, chaos engineering, which is another example of fitness functions. So it's
Hmm.
much more complex, but changes a lot less frequently than unit or functional tests. Because how often do you redefine the core capabilities of your system? Once you've established what kind of scalability I want, that's pretty stable. So a lot of these fitness functions are kind of one and done, and you only have to touch them if you have a fundamental change to capabilities. Whereas unit to functional tests are constantly shifting and changing as you change the structure of your ecosystem. So while they are more complex to build initially, they change much more slowly than traditional kinds of verification mechanisms, because those capabilities we're trying to support change much more slowly than the thing we're building.
Okay. Yeah. Well, let's say someone is listening to this now and they're wanting to get started with fitness functions. I know there's a lot of different tooling and services and libraries and things that are out there that can be helpful for somebody getting started. I also know that all of the ones that you would choose probably depends a lot on your tech stack. So we talk a lot about .NET and JavaScript and things like that on this podcast because that's what we do a lot of at Trailhead.
Yep.
I'm
So let me
curious
give you
in those
So let me
worlds,
give
what
you
are
some
some of the
concrete
tools?
tools for those ecosystems. So
Yeah.
there's a fantastic tool that started a lot of these. So one of the things you can do with fitness functions now is actually validate the structure of your architecture. So
Mm,
if you create a layered architecture, you can write a fitness function that says, don't let developers talk between these layers. Or if you
mm,
build a microservice architecture, you can say, don't let these services talk to one another, but let these services talk to one another. The tools that do those kind of tests, there's one in Java called ArcUnit, but the one in the .NET world is quite mature and very powerful. It's called NetArcTest. That's a tool written by Ben Morris that is designed to allow you to write these structural tests in your architecture.
mm,
Because as an architect, you design stuff, but then you hand this over to developers to implement. How can you make sure they're going to implement it correctly?
mm,
Either because they don't understand the importance of your design, or maybe you're in an ecosystem where it's better to ask forgiveness than permission.
mm,
So a lot of them, how do you govern that kind of stuff and keep it from becoming the wild, wild west? Well, you build these structural unit tests and tools like NetArcTest that says, don't let these two layers talk to one another, but allow these layers to talk to one another.
mm,
The corresponding tool in the JavaScript world is called TS-arc or TypeScript-arc. You can
mm,
write the same kind of structural fitness functions there. And those are compile time checks in many cases where, and this is great because that design that you create takes a lot of effort, and when you start chipping away at that design, you're chipping away at the purpose of that design. So if you
mhm,
design a layered architecture but then people start cheating on the layers, you've lost the separation of concerns, which means you don't really have a layered architecture anymore. You have kind of a
mhm,
ball of mud,
mhm,
and that's probably wasn't your goal to start with when you started that. And so that's another way of validating your design decisions. You can do that within fitness functions as well. Having said that, one of the common problems we find with architects is, so architecture is always different. Architecture is not one platform or technology stack. It's good stuff, it's bad stuff, it's old stuff, it's new stuff. It's We don't even know what that's used for anymore, but somebody touches that database, so we can't get rid of it. Kind of, there's always this stuff. So
yeah,
I've got this problem in architecture now that I want to write our fitness function for. So I'm going to go start Googling to see if I can find someone who's already solved this problem. So that would require somebody else that has the exact same architectures you do
right.
and the exact same problem you do.
Mhm,
And they figured out a beautiful, elegant solution to the problem you have, and then took enough time to write up a nice
yeah.
Medium post about how they solved that and published it for you. I mean,
Seems unlikely.
the Venn diagrams are collapsing into a black hole here. So you're never going to find these things, but you should not give up hope. Almost all architectural fitness functions are 10 or 15 lines of scripting code.
Mm,
Because the real question is, what am I trying to govern? And is the information I'm interested in available somewhere? If it is, I'll write 10 lines of Python or Ruby and aggregate that information together and validate it with an objective measure, and I'm done. So most fitness functions are not written in the tech stack that you're implementing your solution in, but rather little Python, Ruby, Bash, shell scripts, PowerShell, little things that aggregate. So take these 3 log files, aggregate them together, and see if they're talking to one another when they shouldn't. That's a great fitness function, and it
mm,
doesn't require a big heavy framework or a lot of ceremony. It's just a little bit of code that aggregates information that's already at your fingertips. So
mm,
it's a danger to think that you need super sophisticated tools to do this. You do not. And you don't have to be comprehensive. You need to add value to your project. That's what I tell people when they start down this path is, so the way to get started with this is find something on your project that's critical. If it breaks, it's going to be a disaster, and
mm,
write a fitness function around that. And then find the next thing that's going to be, if it breaks, that's going to be a disaster. And you keep doing that until you find something that's like, that's not quite as important. Okay, you're done.
yeah.
You've added value to your project without going crazy and down into some sort of regressive yak shave. So that's exactly
Right.
the place you should be.
Yeah. Yeah. I like that. It's a very pragmatic approach. Stop when you're not adding value.
and always assess, because it takes effort to build these things. The
Yeah.
last thing we want to do is just create meta work. I'm famous for the quote, meta work is more interesting than work. And developers fall into this pattern all the time because it's
Sure.
way more fun to build a brand new framework than to use an existing framework, because meta work
Yeah,
is more interesting than work. So you got to be
that's true.
careful it doesn't turn into that.
Reinventing the wheel. Always
Exactly. Hey,
fun.
reinventing wheels is great. Using wheels is boring.
It is. But a lot faster.
Exactly.
Well, at the time that we're recording this, which is early summer 2024, you've just released a new book. And I wonder if you could tell the listeners a little bit about that.
Yep. So Mark Richards and I wrote Fundamentals of Software Architecture back and released it in 2019, which is an intro book, but there were still a few things that we really glossed over. And so we recently just finished Head First Software Architecture. I'm sure your viewers are familiar with the Head First series, the most famous of which is Head First Design Patterns. But that's a whole series that is owned by O'Reilly, and it's a very different kind of book. I actually refer to it as the ADD guide to learning about something. Because everything is meant to distract you as much as possible. So it is absolutely there are little sidebars, but it's very graphical. It's very interactive. There's exercise every 2 pages to help reinforce all this stuff, and so it's really a kind of an intro guide to a software architecture. Very, very difficult to write though. So Mark and Raju Gandhi and I are the authors of this, and it's 450 pages, and each page has to have a unique title. Every page is custom graphic layout. So it's not really like writing a book, it's like creating a graphic novel. But it was a really interesting process because it forced us to go back and visit some of the things that we kind of glossed over as being too complicated to deal with in our fundamentals book.
Yeah.
Like design versus architecture. We kind of avoided that like the plague in our fundamentals book, but we felt compelled to address that in the Head First book because it's a more intro book, and we did. And I think we gathered some interesting insights because, like so many things, there's not a binary definition. It's a messy spectrum of where it falls on design versus architecture. So some of the things are like strategic versus tactical. Architecture decisions are strategic, whereas design are tactical. A lot of it goes down to how much effort does it take to do this is an architectural decision, and lesser effort is a design decision. So we did a much more diligent work in trying to untangle some of these core concepts. It was really useful for us to kind of clarify some of these things in our head that we've been sort of talking about for a while, but had never really gotten down to the point of writing it down. So it's a great on-ramp to software architecture. And we're finding a lot of developers see software architecture as kind of the escape hatch from AI. And so we're hoping this is going to be a good, gentle intro to software architecture that would lead you to the fundamentals book. So it's kind of an on-ramp to the fundamentals book.
Sounds really valuable. Sounds like a lot of work for you and your co-authors, but really
so
valuable.
Much work. It's just ridiculous how much time it takes, because there are very strict rules about how you can use all these widgets and stuff. You have to audition to write the thing. I mean, I've written 11 books and Mark has written 9 books. We still had to audition to write this thing for the, and so it's a lot of work, but it's very consistent. So part of the value of that series is, they're very consistent throughout. And so it was a very interesting exercise because Mark and I have written a lot about software architecture. So taking it and bending it like that was a fascinating process. And I think we uncovered some insights in that book that we had not touched on before. So that's the real value from us to do something like that.
I'm definitely looking forward to checking that out. I'm sure a lot of people listening or watching this are feeling the same way. So thanks for putting that together. One last question I have for you, just to wrap things up, which is a question I ask all of our guests. So as you know, the theme of this podcast is making software projects more predictably successful. And we've been talking about fitness functions today as a way to do that. What other topics or guests do you think would be valuable to talk about or talk to on the podcast?
So I know 2, and interestingly enough, they span, I think, something that Mark and I realized a few years ago, and I think the entire development world has reached the realization in varying degrees of impact so far, is how important data is to software development. For too long, we just sort of treated that as a different world and different thing. But when you get to things like microservices, it's critically important. And in
Hmm.
fact, there are two critical aspects that you need to think about: operational data and analytical data. Both of those things are terrifying in complexity compared to a lot of our other stuff. And so my suggestion here is promote Sadal Gay for operational data. He's the one that wrote the Refactoring Databases book, which
Hmm.
is still by far the best-selling database book for developers probably ever, with
Hmm.
Scott Ambler more than a decade ago. He's also a co-author on Software Architecture, the Hard Parts. He's an expert on operational data and coined the term refactoring databases. People, when he started talking about that, thought it was impossible. And he showed
Hmm.
them, yeah, it's possible. Not only is it possible, you need to do it. And it was interesting because he released that book in like 2010. And, it had the normal kind of spike and then kind of graduate. And then microservices came out and the sales went through the roof again because
Yeah.
suddenly everybody's got to refactor databases. So, and he's so knowledgeable. I mean, he's the most knowledgeable person I've ever met about the intersection of engineering practices and operational databases. So he's great. And the other one that I think is worth talking to is our other co-author in the Hard Parts book, Zhamak Dehghani, who's created this thing called a data mesh, which is a really clever solution to a long-standing problem of how to deal with analytical data. This is mostly just a teaser, but basically what she has designed is an aspect-oriented architecture that sits on top of your operational architecture with well-defined join points. And these two architectures kind of work independently of one another, using the operational data to derive the analytical data through a very well understood data pump kind of setup. It's really clever, and it really does give you what aspect-oriented programming give you, which are cross-cutting concerns at the architecture level. This allows you to do this in distributed architectures like microservices. So
Hmm.
it's one of the most elegant solutions I've seen to this analytics problem, and I've been dealing with it for 30 or 40 years professionally, and this is the best. It's not perfect, but it's the one that's most closely aligned with the kind of architectures we're building now. So
Wow.
I think both of those guests would be fascinating because they both exist in a very nuanced, very complex world that's often foreign to
Hmm.
developers and architects.
Yeah, that's great. And we haven't talked a lot about data on here yet, so I think those would both be awesome guests to get. So thanks for that suggestion. Also, thank you for your insights and experience on this fitness functions topic. I think this has been a really valuable and helpful conversation, uh, and really appreciate your time and getting
It's
to
been
have
my
this
pleasure.
combo with you.
Yeah, great. Thanks for
Thanks so
having me.
much, Neal. That's the end of this Blue Blazes podcast. If you're interested in hearing more conversations like this one with industry experts focused on how to make software projects more predictably successful, make sure to subscribe. Trailhead can be found online at trailheadtechnology.com, on Twitter, LinkedIn, and Facebook. Until next time, thanks for listening.